to our third video in Unit 2 of Integrated Math 1. Like always, we'll get started with the warm-up for today, and then we'll get into our lesson. So go ahead and try these 5 problems, and as you're doing so, try to use some mental math as you go, and then we'll go over them here in just a second. Okay, so number 1 here, absolute value. Start with the inside and then work your way out. So 3 times negative 2 is negative 6, plus 1 is negative 5, and then the absolute value of that will be positive 5. The absolute value is really the distance that number is from 0. So negative 5 is 5 units away from 0. And so that would be 5 minus 2 is 3. So we should be getting 3 there. Number 2 is kind of an interesting problem. As we've been talking about the last few videos here, arithmetic sequence. This is an arithmetic sequence, but we're adding up the numbers in an arithmetic sequence, which is kind of interesting. So you could have done some mental math and added all these up, or you could have noticed that there are pairs of, a bunch of pairs of 19. In fact, 3 pairs of 19. So 3 times 19, if you can do 3 times 20 first, which is 60. So 3 times 19 would be 57. So this should add up to 57. It's kind of an interesting strategy there. Anytime you have an arithmetic sequence and you're adding those up, you can kind of pair them off, and it will always add up to the sum of any one pair times the number of pairs you have. Number 3, what is the next term in this sequence here? If you notice, we're subtracting 13. Subtracting 13. So subtract 13 one more time, and you'll get, let's see, subtracting 13. Let's see, subtracting 11 more would give us down to negative 30, so negative 32. We can also think about what the sequence that would be, or the formula that would be involved here, as we did in the previous video. So that would be a sub n equals 7 minus 13 times n minus 1. Again, if it's decreasing each time in the arithmetic sequence, you're going to have a negative common difference here. So it's going to be minus 13 times n minus 1. Again, I didn't ask you to do that, but just to kind of give you some a review of what we've been doing. Number 4, 468 divided by 0.468. We've done one like this before, where you want to think about this as multiplication instead. So whenever we're dividing two things, really you can think about the denominator times what produces the numerator. And so if you multiply this times 10, that's going to move the decimal place this way, times 100 times 1,000 would give you 468. So it's actually 1,000 is the answer. Number 5, 6 to the negative first power. We've looked at this pattern before with exponents, but we'll go over it again. 6 to the third. Let's start with the second. 6 squared is 36. 6 to the first is 6. 6 to the 0. Let's see if we continue this pattern. We're dividing by 6 each time we go. So if we divide by 6 again, we're going to get 1, which makes sense because anything to the 0 power is 1. And then let's just take it one more step further. We could go to the negative first power. That's going to be 1/6. We divide by 6 again. And it kind of reminds us that the negative first power is just the reciprocal. So just flip the fraction there, and that should give us your answer as well in a different way. So any questions on those 5? Hopefully a good reminder of some different things there. Okay, so as we get into our lesson for today, our goal, we have 3 of them. One is to explore arithmetic sequences further. So we looked at them last time with the calendar. We looked at time before with the corral problem. We're going to expand on those a little bit further today. Understand and explain an interesting property of arithmetic sequences. So we're going to find an interesting property today of arithmetic sequences. And then lastly, understand the process of reasoning and justification in mathematics. So there's kind of a way that we can kind of go about reasoning and justification and proving things in mathematics. So we're going to look at that today. Okay, so you might remember this from last time. This is the calendar that we looked at in our last session. We have already looked at patterns because we thought about maybe like adding 8 diagonally down to the right, adding 6 diagonally as you go down to the left, adding 1 as you go across, adding 7 as you go straight down. We found a lot of patterns in our last video, but we're going to expand on those in this video. So last year I had a student that came up with an interesting trick regarding numbers. And here's what he said. He said, if you give me the sum of any 3 consecutive days, so if you add them up and you give me the total, I can quickly tell you what 3 days you were talking about, what 3 days you added up. So I want to give you a chance to try this. So I want you to find 3 consecutive days up here and add them together. And then here in just a moment, I'm going to have you tell me what the total was and see if I can guess what 3 numbers you added up. Okay, so take a second to do that. Okay, so do you have a total? What is a total that you want to give me? You get one? 35. So 35. Try it one more time.
Uh,
45. Okay. So 45. Let's see. Then you've got 14, 15, and 16. Is that right? Okay. Anybody else have another total? 63. So you're working with 20, 21, and 22. Anybody else want to try? 27, 8, 9, and 10. You did 27. Did you do one? That one too. Okay. So we kind of wonder, like, how can we do this, right? How could this student have come up with this idea and like just like that tell you what 3 numbers you were working with? And so that's what we're going to get into today. So you added up numbers in this pattern here. So 3 consecutive numbers. So we talk about this frame being what you worked with, right? So one day with another day here and then another day there. That's what we're working with starting out here. So our observation, let's see, did any of you figure out how I was doing that? So one of you said 27, and automatically I knew that the middle number was 9. So that told me that it was 8, 9, and 10. You told me 63, so right off the bat I knew the middle number was 21, so then I knew that it was 20 and 22 on either side.
Do you divide by 3 because there's 3 numbers?
Divide by 3, exactly. So if you were to tell me 90, then I know your 3 numbers and I know 31 is not up here, but it'll be 29, 30, and 31. So yes, divided by 3. So we're going to figure out like why that happens and how that works today. So our conjecture is that we take the sum. So we take the sum divided by 3, and that equals the middle number. We're going to call m. We'll call the middle number m. All right. And in the same way, that means the sum is equal to 3m. Right? The sum that you gave me was 3 times that middle number. So that's what we're going to want to prove today, is that that is indeed the case, and will always be the case, no matter what 3 numbers you worked with. Okay, so let's try this first one together, and then I'm going to let you explore maybe a different frame. Instead of 3 in a row, you might do like 3 diagonally or something like that. So let's look at this first one together. So let's call the middle number m. If that middle number we call m, how would you write the number before it using m, not necessarily like another variable. What would you, what would we call it? Yeah, what's the relationship? It's one less than m, right? So we're going to call this one is m minus 1, and then the next one after would be m plus 1. Okay? So then let's see if we can actually add these together and see what we get. So m minus 1 plus m plus m plus 1. You see something nice that happens here? The plus 1 and the minus 1 are what we call additive inverses. They add together to give you 0. And so all we're left with is m plus m, which is 3m. So the total, if we add them together, or the sum, is 3m. And that will work no matter where you think about putting this frame in the calendar. It will always work because of this justification here that we've provided. Does that kind of make sense? So that's a special property with any arithmetic sequence, as we're going to see here in a minute. It doesn't have to be just plus 1 and minus 1. We're going to see here in just a moment that works for any of them. Okay, so let's try this with a different frame. So now we've got 3 in a column instead. So take a second, and I want to see if you can figure out, does this idea also work for 3 in a column? Can I take the sum and divide by 3 and figure out what the middle number is? So take a moment, see if you can, again, provide justification, but for this frame instead. Okay, yeah, so if we look at this one, we're going to have m in the middle here. M minus 7, because we know that we're adding 7 each time along the column there. M minus 7 would be the one above it. M plus 7 would be the one below it. So our justification here to show that the sum is always 3 times the middle number would look like this. M minus 7 plus m plus m plus 7. And add those together. Again, the 7 and the negative 7 are additive inverses, so that would just give us 3m. So the sum is equal to 3 times the middle number. So in our next example here, we're going to look at a variety of different selection frames. So here we have 3 in a column. Earlier we looked at 3 in a row. But there are a number of different setups or frames that we can look at to analyze and see if they follow the same idea. And so we're going to do that now. Okay, so in this next example, I want you to look at a different frame. And so those of you watching online, if you'll use this as your frame, and we've got a little bit different setup here than before. It's not the calendar anymore. We're going back to those odd numbers that we looked at last video. So we try to use this frame here and see if you can figure out a way to prove or disprove maybe a conjecture that you have about this one. So 3 in a row with 3 in a column at the same time. So see if you can do that. Okay, so we have a bunch of other frames as well that we looked at in the room here, and we're going to go through all of these together. So if you notice, first of all, some patterns here. As we increase in the column, we're adding 12 each time. As we increase in the row, we're adding 2 each time. Diagonally this way is 14. Diagonally this way is 10. So just some common patterns there that we're seeing throughout. So if we look at this first set of 5 here, we might think that it's maybe still 3 times the middle number. Who knows? So let's see if we can figure it out. And so I think one of you had this one. You had this one, right? So what did you do for this one? Uh-huh. Okay, so you thought about like this being m, so then this one here would be m minus 4.
Yeah.
Okay.
And I added them up, and then when you write them, they equal n because the way that
Okay. Yeah, so the first one is 4 less than the middle number. The last one's 4 more. And what about these two?
The next one is minus 2, and then that one is plus 2.
Okay. So we have the middle number minus 4, middle number plus minus 2, the middle number itself, and plus 2 and plus 4. So if we were to add all these up, the minus 4 and plus 4 would simplify to 0. Negative 2 and 2 would also add to 0, leaving us with how many m's? 5. So this tells us that the sum of these 5, any five in a row, is 5 times the middle number. And so if you were to give me the total, I would divide it by 5, and that would help me figure out the middle number. Okay, so let's go on to one of these other ones here. So if this one here, 3 diagonally, if the middle number here is m in the middle there, then what would this one be?
It'd be n minus 14.
N minus 14. And this one?
N plus 14.
Plus 14. So the sum of them would be 3m. So 3 times the middle number is the total there. All right. How about this t here that those of you that online worked on as well? If we call this m, then the one before that is?
The one above it is n minus 12.
Okay, m minus 12.
And then under it is n plus 12.
Okay, so that balances out nicely, doesn't it?
And then on the sides, n minus 2 and n plus 2.
Okay, and so when we add those together, these two add to 0, these two add to 0, and how many m's are you left with?
5.
5m, so 5m. So we might be thinking at this point, at least we have a conjecture about if we have 5 boxes forming a frame, that it would be 5m that is the total. So that's maybe our conjecture. If we have 3 boxes, then maybe it's only 3m. So maybe this number out in front is the number of boxes making up our frame. So let's test this with a couple of other ones. So we have 4 boxes here and we have 9 boxes here. Let's start with 9 boxes. So if m is the middle number, it would be this middle one here, and then we can fill in the rest here. As we saw a minute ago, diagonally is the 14s. So this would be m minus 14, m plus 14. Diagonally this way is how much?
N minus 10.
Minus 10, and m plus 10. And then vertically is
N minus 12.
minus 12 and plus 12. And then horizontally,
N minus 7 and N plus 2.
and really this frame is kind of a combination of all the other frames that we've done, right? And so this kind of puts it all together now. So the minus 14 and plus 14, the minus 12 and plus 12, minus 10 plus 10, minus 2 plus 2, all of these, the numbers at least, add to 0, leaving us with how many m's? 9. So the sum of all of that is 9m. So that confirms our conjecture that we had a minute ago of it being the number of boxes in the frame. But let's go to maybe a different scenario, because we've only worked with the odd number of boxes here. If we go to the even number of boxes here, you might find some issues there. Did you find some issues? What happened there?
They don't balance out.
They don't balance out because maybe there's not a middle number, right? If you were to call this m, and this would be m plus 2, and m plus 4, and then this one's m minus 2. So it doesn't really work that well with an even frame. Yeah, if there's an even number of boxes in the frame, it really doesn't add up to the middle number, it adds up to the middle of the two middle numbers. So if we were to have maybe 5 and 7 here, then the average of those four numbers would actually be the middle of those two, so it'd be 6 instead. But for an odd number of numbers, what we're finding here is that the sum will always be that number times m, which also tells us something else significant about these arithmetic sequences. And it is that the average of all of these numbers in making up these frames, the average of all those numbers is the middle number. So if we were to go back and look at something up here, I think somebody looked at these first 5 here. What would be the average of 1, 3, 5, 7, and 9? What's the average? 5. Because we know that the sum divided by 5 should be the average, right? And if we know that the sum is 5 times the middle number, and we divide by 5, we get the middle number. So that means the average is the middle number, which is something really special about an arithmetic sequence. So if we were to have this sequence here, and I just asked you real quick, what's the average of all these numbers? Yeah, 31, the middle number, right? You don't have to add them up. You don't have to do anything. All you got to do is check that it is an arithmetic sequence and find the middle number, and that's the average. Something special about an arithmetic sequence is we have this balance going on, as we've seen today in the frames that we've been working with. And so that's a really special property about arithmetic sequences. And so we've got this one here. And again, to review, this one would be, in terms of a formula, 7 plus, 8 times n minus 1. But again, we're seeing special properties about arithmetic sequences in this session. And so hopefully we were able to reach our goal for today. I want you to think about a couple things here real quick before we finish up though. What was most meaningful about today's class? And then in general, what do you think are the major steps of exploring patterns are? So take a moment to do that. Think about these two questions. Okay, so number one here, you probably have a lot of different things that are meaningful. Hopefully you walked away with some different things from arithmetic sequences in terms of the average being the middle number, and some other things, but also exploring patterns in calendar and that kind of thing. If we look at number 2 here, what do you think are the most major steps of exploring patterns? So if we think about these steps, we've first made a conjecture, like we think that it's 3 times the middle number, or we thought it was 5 times the middle number, or 9 times the middle number. We started with a conjecture, and then we tested that conjecture. You probably typed in some numbers to see if it actually worked, and then lastly we justified. Like we used algebra to come up with expressions and added them together to show that it works for any set of numbers. And so those are the 3 main things here. To create a conjecture just by looking at patterns, and then test that conjecture with data and numbers, and then to justify it using algebra. And so those are the 3 major steps that we went through today for exploring patterns. And so again, hopefully we're able to reach our goal for today, which was to explore arithmetic sequences further, understand and explain an interesting property that we saw today, and then understand the process of reasoning and justification, again, through those 3 steps that we went through today. All right, so that's it for this video. I hope you'll join us next time for video 4 in this video series.